I hope I'm audible.
Yes, ma'am.
Yeah, right. Thanks. Okay. Good. Today we will solve some problems based on week 9. Compensator design based on Bode. You would have already done compensator design based on root locus. Now we are going to use different methods to do the same compensator design. Uh, so far, root locus method that is based on transient characteristics, right? Transient characteristics given in terms of time domain specifications. For example, rise time, peak overshoot, settling time, etc. But now what we are going to do is using Bode, we are going to translate this transient response or transient characteristics indirectly and try to design a compensator to meet the specifications. The ultimate aim is to make the system to meet the specifications, but there are different methods or different types of solving the problems, different viewpoints, maybe from time domain, that is a direct method. Now we are going to use the frequency response method, which is easy to design, but the parameters are being explained indirectly here. That is the only main difference between these two. So when you see the frequency response plot, that indicates clearly that in which system it should be modified or how it should be modified. Although the exact quantitative predictions of the transient responses cannot be made. This frequency response approaches can be applied to any systems or components whose dynamic characteristics are given in terms of frequency response data. For example, phase margin, gain margin, phase crossover frequencies, gain crossover frequencies, peak overshoot in terms of um, in relation to the gain. So that kind of data you can use for those kind of data you can use this Bode based design. So the in frequency response design we would have studied two different methods, right? One is Bode, another one is Nyquist plot, otherwise called as polar plot also. So when compensator is added to any system, the if you use a Nyquist plot, that does not retain the original shape, and therefore we need to draw a new Nyquist plot every time when we make some changes in our design. So this will take some time. On the other hand, if you use a Bode plot, it can be simply added to the original Bode diagram. Thus, plotting this Bode diagram will be very easy. So, if you fine tune your open loop gain, for example, you will be given with the open loop transfer function, right? If you just change the open loop gain, the magnitude curve will be shifted up and down. For example, if this is the magnitude plot for a open loop gain of k equal to 0, for positive gain values, changes in the gain values that are positive, the magnitude plot will be shifted up. For negative values, this will be shifted down. So these are the major changes you would expect in a Bode plot, unlike in your Nyquist plot. So varying gain will just shift the plot, does not change its frequency characteristics or its phase characteristics. So using the Bode plot will be much easier than using the Nyquist or polar plot in this case while designing a compensator using the frequency response characteristics. That's why we used to choose this Bode plot. Second important point I want to mention is while designing a Bode diagram, we'll adjust the open loop gain. At first, the first attempt to make, for example, if you are given with the open loop transfer function, and you will be given some specifications. For example, the specifications can be of both steady state and transient response, transients based. Steady state would be kind of your velocity error constant or position error constant or what else? Acceleration error constant should be this kind of specification they will give. Transient characteristics will be in terms of phase margin, gain margin. You have to attend this much gain margin, this values of phase margin. So these are all the requirement in terms of transient responses. So first of all, how do we attempt to achieve this specification? First of all, we'll try to change the open loop gain. This is the simplest of all. So first, we'll try to change the K value and see whether the system attain this requirement, whether the system will be able to give the expected requirement. If not, then we will try to add a pole or a zero, and when to add a pole, when to add a zero. So if I want to shift the pole more towards right or towards left or even farther or closer to the zeros, this like what to say, this play around will be classified into a lead compensator or lag compensator or lag lead compensator based on how we want to design. This is the whole nuances of the designing a compensator based on the specifications. Right. First of all, before designing itself, we want to know how our system should look like, or how whether the system is will be able to compensate or not. That information we need to know, right? For that, we have few already derived terms. In many practical cases, compensations is essentially a compromise between the steady state accuracy and relative stability. So you have to find a suitable compensation that can achieve both of this. So there will always be a trade-off between this. If you focus more on your steady state accuracy, you might lose relative stability. If you focus more on relative stability, you might lose steady state accuracy. So you should be able to design a compensator that achieves both of this with a proper trade-off. This is the first point. The second thing to notice is to have a high value of velocity error constant. For example, I want to design a KV greater than 50, greater than 100, something like that. Someone ask any question or something? Or just join? Okay. Right. Yeah, to adjust your system based on your velocity error constant, if the velocity error constant is very high, and to get a satisfactory relative stability also, you need to reshape your open loop frequency response so that you will achieve the compensator system, right? For that, the minimum required we would expect is that the log magnitude curve, in the log magnitude curve, the slope should be minimum minus 20 decibel per decade. So in this manner, this is the minimum requirement you would expect. If your system can achieve at least this, then only you can say there is a possibility to compensate for. Otherwise, it is not at all possible to make your system pull towards left or right, your body towards left or right at all. So your slope should extend over a sufficiently wide frequency frequency range to attain this proper phase margin, whatever requirement it is. And for there are in the Bode plot, you would see there are it's a log magnitude plot, like maybe this 0, 10, 100, 1000 it would go. So these are all low frequency ranges, and as we go further towards right, that will you will have a high frequency range, and somewhere in between we will have mid frequency range, right? So you already would have seen this in the PPT, I guess, how this frequency ranges would affect. For example, this low frequency ranges, this affects your steady state behavior. This region is responsible for deciding how your steady state behavior of the system would look like. And this mid frequency range, This will dictates the relative stability of your system and also the transient response of the system or of your closed loop system actually. Okay. And the further range, that is a high frequency range, this there, if there are much gain or the gain you have in this region for high frequency range that is of very high magnitude, then you need to attenuate this gain so that you will get a noise free system. Otherwise this will increase the noise or the disturbance in your system. So when you want to fine tune your steady state response, you will look in this region. So how can you compensate or how can you design another compensator so that you can adjust the Bode or magnitude Bode magnitude plot of your system high or low or shift towards left or right so that I can get the desired steady state response. If you want to focus on your transient response, for example, phase margin, gain margin, you want to adjust in this region. So how you want to design a system so that I can pull off the desired transient response. So these are all the important things when you want to change your open loop responses to get the desired response. Okay. In general, you already would have known about this. So in general, we have three types of compensation. One is lead compensation, lag compensation, and lead lag compensation, right? So when to use what, how to design this compensation. That's what we are going to see with an example today, step by step. First of all, I want to start with the lead compensation, just to give you some idea about its structure, about its utility, and what are all the changes you can make to get your desired responses. First of all, a lead compensator structure would look like this: Kc S plus 1 by T divided by S plus 1 by alpha T. Whereas your lag compensator would look like same with the range of beta. Instead of alpha, we used to mention that as beta. S plus 1 by T divided by S plus 1 by beta T, just to understand the difference between these two, not to get confused one with each other. This would look like the same. Right. So the difference between these two is here alpha will be, here beta will be always greater than. So this is the minute difference between these two. Alpha will always be lesser than 1 but greater than 0. Beta is only upper bounded, that is always greater than 1. That's it. So if you design the same structure with the values that alpha time constant, the variable lesser than 1, you would expect a lead compensator. If you put the alpha value greater than 1, you will expect a lag compensator. That's it. So when can we choose the value lesser than 1 and when can we choose the value greater than 1? So that is of our interest, right? Okay. This is an in between topic. Okay. When you have a low phase margin in your system, so the solution would be you want to add phase margin or add phase. So this is plus. So you want to shift your Bode plot towards, when you want to add phase, you would generally shift your Bode to left so that the phase will be added. If you shift your Bode towards right, the phase will be decreased or subtracted, right? So in this case, you tend to choose a compensator that is lead type. So when you expect a problem that has poor steady state value, so you want to improve the steady state value. Your steady state value of the uncompensated system is very low or very far from the expected one. Then you would do add a low frequency gain. This will enhance your steady state value. As we discuss here, if you want to focus on steady state, you would expect some change in this low frequency region. Therefore, we will add some low frequency gain. At that time, lag compensator will be helpful because it is dominating for the steady state characteristics. So when you want to do both, like the phase margin expectation is also very bad, steady state expectation is also bad. In that case, you would do both. So you would go for lag plus lead compensation or lead lag lead compensator. Both are same, right? So these are all the requirements in between. Good. Now we will start off. Another thing I want to tell is the difference how the lead lag compensators would look like. Right. Here in lead compensations, as we always do alpha value in between 0 to 1, for small values of alpha, like towards 0, the pole will be located very far from the 0, right? In case of lag compensation, the 0 will be located very far from the pole, right? So by placing this pole and 0 at proper location, we will get the desired output response or desired transient or steady state response. This is what we did in the PID controller also. We would change the gain of the P, I, and D, excuse me, individually, so that we will place the poles of the overall closed loop transfer function by changing the gain. Then we will get the desired output response. The base for all the techniques are same. We ultimately we want to keep the pole and 0 at proper place so that we will get the desired output response. So the tools we use to do this changes for each and every chapter. Before it is PID controller, after it is root locus, now it is Bode plot and Nyquist plot, etc. Right? And then, okay. Okay, I think you are familiar with all the formulas like maximum phase, sine phi m and all. So if not, you can go through the PPT, but we can understand what they put while solving the problem. Otherwise, it will take a lot of time. Start with one example from lead compensation. For example, I am taking this open loop transfer function that is 4 by s plus s into s plus 2. My requirement is that you want to design a compensator so that your static velocity error constant kV is 20 second inverse. Don't worry about the unit for now, but kV should be equal to 20. That's what the first specification is. Second specification is phase margin is at least 50°. So phase margin should be greater than or equal to 50°. The third criteria is the grain margin is at least 10 decibels. So gain margin should be greater than 10 decibel. Okay, right. Now the first step is First, we always look to compensate the steady state error or characteristics. Then we will go with the transient responses, because sometimes when we change the loop gain, that itself will give a expected outcome. Sometimes it's very rare, I know, but we will just start off with that so that that won't be hard at the later steps. Okay, first, just rewrite the system in terms of by adding the gain also. Right now, with the given specifications, okay, with the given specification, we are going to derive the K value. For KV, the expectation is 20. So we will use this KV equal to limit x tends to 0, s into g of s. This will give us 4k by s into s plus 2, right? Now this is 20, 20 equal to 4k by 2, 2k, 20, k equal to 10. Right. Now we found the open loop gain. The overall uncompensated system is 4, 10, 40 divided by s into s plus 2. This is your overall uncompensated system. Now the second step is to plot Bode for the uncompensated system and check the specifications. Write like this: uncompensated system, specification, and required specification. Required, 20 kV equal to 20, phase margin should be greater than 50, gain margin should be greater than or equal to 10. Now, write the phase margin and gain margin of the, sorry, phase margin and gain margin of the uncompensated system. You would expect in the assignment itself, you would be asked to solve it analytically first and then check it with the MATLAB. So you know how to find this phase margin, gain margin by hand using the Bode plot during the previous week's assignments. So just try to find it by hand at first. I'm going to use MATLAB for now. I will present my screen like to show the MATLAB one. I have to switch between this laptop. I'm sorry, laptop and iPad. Bear with me. Okay. I hope this MATLAB window is visible now, right?
Yes, ma'am.
Right. Thanks. Okay. Now, if you see, this is our system. Previously, I used to write the transfer function as 40 divided by s into s plus 2. This is your transfer function. Okay, so I have written in terms of transfer function. This is the coefficient of the numerator. Denominator would be s square plus 2s. So I write in terms of s square, coefficient of s square, 2s and 0, because there is no term in the constant term. So I put 0 for this. So if you see this, yeah, you would see this, right? 40 by s square plus 2s here. Okay. Right. Now I'm going to plot the Bode plot for this. When I plot the Bode here, I think the Bode is not visible for it. I will present the window. Mm. Now, in Bode, if you want to see the characteristics, you can right click on this Bode diagram go to characteristics and all stability margin. If you do that, you will see the stability margin. Since there is no point here, you can understand that it is the gain margin is infinity. And if you click on this phase margin or phase plot, the dot, you will see the phase margin value here. Here the phase margin is 18, but our requirement is minimum 50. So this is very far from your requirement. That is the first understanding we are making. Right. The gain margin should be at least 10, but it is infinity. This is too much, but satisfying the requirement. So now we are going to worry about only the phase margin. We want to increase this phase margin from 18 to 40. That is our first objective. Right. Now,
Excuse me, ma'am.
yeah.
How are we saying gain margin is infinity?
Oh, okay. Here you cannot see that this
Dot.
kind of dot. So it is at infinity.
Okay.
You cannot see that. That's why.
Oh, okay.
Okay. Right. Now, right. I'm switching my tab to explain you that. Okay. Now the phase margin is 18 degree and the gain margin is infinity. Gain margin is infinity for now, but we have to make it push this to 50 somehow to design a compensator. Now, as we saw here, if you want to, where is that? Dabba? You want to add phase margin is 18, you want to make it at least 50. So if you want to add phase, we will use a lead compensator because that will shift your lead compensator based on your alpha value. That will shift your Bode plot towards left. This will increase your phase. That's the intuitive way to understand this. That's why we are using the lead compensator. Right. Lead compensator, we know it will be in terms of this. We are going to design a compensator that looks like this. Whose transfer function will look like this, right? Right and right. Right. Good. Now there are values you want to see. So the only one unknown you have in this is alpha. So how are we going to design this alpha? That is our next motive. Right. Now, this phase margin that is of 18 degree, that implies that the system is little oscillatory. So the satisfying the specification on steady state yields a poor transient response performance. When you try to do something to the steady state so that if you achieve this phase margin, then this will give you a very bad transient responses since it is oscillatory. So the specification needs a phase margin phase margin rise between 50 minus 18. At least it should have 35 over 35 degree rise, right? Okay, the exact thing you want is 33 degrees, but over 35 would be fine. To achieve this phase margin of 50 without decreasing the value of K, the lead compensator will be contributed, like that will contribute the required phase angle. The addition of this lead compensator will also modify the magnitude curve of your Bode diagram, that we already know that, and that the gain crossover frequency will be shifted to the right. So if you want to offset this increased phase lag due to the increase in the gain crossover frequency, we have to be careful while designing the alpha value. Considering the shift of this gain crossover frequency, like omega GC, we may assume that maximum phase lead require is approximately 38 degrees, because we need 33, but we always have this 5 to 12 degrees increment, because this will increase a lag in the phase, right? As we discussed, the gain crossover frequency will also change. If you shift your Bode plot towards your right, this will introduce one lag. To compensate for this lag and also to achieve this record specification, we are going to add some 5 degrees increment, and we are going to try to design a compensator for this 38 degrees instead of 33 degrees. Is it clear? Like, any doubt in this? We always have this increment of the requirement, because to compensate for the lag it is providing in due to the lead compensation, right? Okay, and we know the formula to find the maximum phase lag that relates to the alpha value is 1 minus alpha 1 plus alpha. This will also be written as sine inverse of 1 minus alpha by 1 plus alpha. Okay, now phi m should be 38 degree minimum. So 38 equal to sine inverse of 1 minus alpha by 1 plus alpha. So if you do this, otherwise it will be easy to keep it here itself. So sine 38 degrees, so sine 38. I hope this is in degrees. So this will give you 0.615. 0.615 equal to 1 minus alpha by 1 plus alpha. This will give me 1 minus alpha equal to 0.615 plus 0.615 alpha. So 1 minus 0.615 minus alpha plus 0.615 alpha equal to 0. This is 1 minus 0.615, how much it is? Point 385. Alpha equal to 1. Let me check once. No, it won't be 1.
No, ma'am. It will be 1 minus 0.615 minus alpha minus 0.615 alpha, right? Like alpha.
Okay, this is
Alpha
plus,
comes
right?
ahead.
Yeah, right. So this will be plus minus, correct?
Yeah.
Okay, right.
Then it will be like something 0.23 around alpha.
Okay. What is the alpha value? 1 point, okay, right. It's easy to calculate. 0.385 minus 1.615 alpha equal to 0. 1.615 alpha equal to 0.385. Alpha will give me around 0.25 something, right? I guess so.
Yes, ma'am.
Okay, now we determine the alpha factor. We know this sorry, this how this transfer function will look like. S plus 1 by t by 1 plus S plus 1 by alpha. Alpha we know. Oh, alpha and t we don't know, right? T also we have to find. So to find the t, we need to find the close relations. First, how we can do is, once we know this alpha for now. So next step is to determine the corner frequencies. The corner frequencies are for lead compensators. It is omega equal to 1 by 2 and omega equal to 1 by alpha t. So usually the maximum phase lead occurs at the geometric mean of these two corner frequencies. For example, mean of 1 by t comma 1 by alpha t. Between these two only the maximum phase lead will occur. So if you know the maximum phase lead, we can relate to this 1 by t and alpha t geometric mean, so that we will get to know the t value. Right. Now this I can say in between, if you take a mean in between this, you would end up having something like this. If you multiply and divide and add some both of this and get a mean, you would get something like this. So the amount of modifications in the magnitude curve at omega equal to 1 by this value, due to the inclusion of the term that ts plus 1 by 1 plus ts into 1 plus alpha ts, this denominator here. Here. In terms of the, oh, sorry, okay, right? So I otherwise I will write like this. It will be easy to interpret. Okay, right. Now, if I write it in terms of frequencies, yes, wherever it is yes, I'm just replacing it with j omega. This has been written like this for ease of calculation. Omega should be at 1 by alpha t, because phi m occurs at this frequencies. This is the mean of those corner frequencies. So this will give me, if I put alpha t, t will get cancelled, and I would be having 1 by root t, root alpha, divided by 1 plus j alpha root alpha. Then I would have alpha into 1 by root alpha. T, both t will get cancelled. So this will give me, what else there? If I take alpha, this would be 1 plus j by root alpha divided by 1 plus j root alpha. So if you take a magnitude out of it, square, if you put a root and square, you would be having 1 by root alpha. So you know alpha value, right? Alpha is equal to 0.25. So if you have 1 by root alpha, this will be 1 by root of 0.25. This will give me this 0.25 root 1 by 0.5. 2. Right. I will have 0.25. Why am I getting 2? It is not supposed to be 2. 1 minute. 1 divided by
By 0.5 will be 2. Root over 0.25 is 0.5.
yeah.
1 by 0.5 means 2. 1 by 1 by 2.
Right, 2. But in terms of decibels, if you find 2 log of 2, 20 log of 2, right. If you take, this is a magnitude, right? If you take 20 log of 2, you would have 6 decibels. Right? We need in terms of decibels to adjust the frequency, right? So you have to see, because in the magnitude plot, you would be having only in terms of decibels. That's why I'm changing it to decibels. So you have to see your magnitude of G of j omega whenever it is around 6 point or 6, maybe 6 decibels, around 6 decibels, you have to note the frequency. What is the frequency around it? So I'm just seeing whether around 6 decibels. I'm just dragging the cursor over my magnitude plot and see. This is 3, this is 3. 5.58 is 4.37. After that, I couldn't take. So it's around 4.37. I want. Let me try to take it accurately. Say it right. Okay, the frequency is around. Oh, sorry, this should be minus, right? If you take a value, we have to find it in terms of minus 6 decimals. I was looking in a wrong direction. 13 minus around minus how much it will be. Okay. These are all the 2 points I was able to find. For minus 7.3, it is 9.56. For minus 4.7 magnitude, it's around 8.18. So in between, if I want to find around 6, I am assuming that it must come around 8.8. 8.8, like around, I'm just taking around 8.8. So 9 radians per second I'm considering. Okay. Omega. So the first of all, you're finding the first step is you're confused. First step you are finding alpha. To find T, you have to somehow relate the known values. What are all the known values? Only alpha we know. And with this alpha, how can we find the T value? So the step is first find the maximum 5 m where it occurs in between two corner frequencies, that is 1 by t and 1 by alpha t. If you find a mean between 1 by t and 1 by alpha t, you would have 1 by root alpha value. So at that value, find the frequency of that value, so that you are going to select this frequency to be your new gain crossover frequency. So this omega becomes your new omega GC. Previously, the gain crossover frequency, how much it was? It was 6.15. Okay. Now we are choosing this omega GC as 9 to because the body have shifted forever requirement. So we are finding this omega GC in terms of our alpha that we found to compensate for our requirement. That is around 50, greater than 50 degrees of phase margin. Right. Now, omega we have considered is 1 by root alpha t. That is a mean of the two corner frequencies. Omega c. This is also a corner frequency. So we know this 1 by t relation between this omega c and t is root alpha into omega c. Right. Omega c we know. So alpha we know. What is alpha? Alpha will be around 0.24 root of omega c. We are taking 9 1 by t. So now 1 by t we can directly put this value, right? This will give you around 4.4. Right now, you just find the 1 by alpha t to fill the transfer function. 1 by alpha t will be 1 by, 4.4, 4.4 divided by 0.24. This will give you around 18.4. 1 by alpha t. Now we know all the information. 1 by t we know 4.4. 1 by alpha t we know 18.4. And this is your whole system. Like this. S plus 4.4 divided by S plus 18.4. This is your designed compensator. Now, what you are trying to do is You have DFS. You now design a GCFS. This is your RFS, YFS, HFS. So you go back, there will be some summation. So you are going to find this G into GC. You are going to replace your G with this G into GC. So your overall, so for that you need to find the gain value also, right? Sorry, I missed this. There must be some gain values, KC. So you have to find that K value. Kc will be K by alpha 10 by 0.24 divided by 14.7, around it will come. So your new designed gain compensator into G is G you already know 40 by S into S plus 2 into 41.7 into S plus 4.4 divided by X plus 18.4. So this is your overall system after compensator. Now I have replaced this DC with G. My MATLAB screen is also visible, right? Or should I will, okay, resume present. Right. Now it is visible, I think. Okay. Right. Now, yeah. Now I have replaced, this is the overall transfer function. Just instead of this into S in terms of that, I have calculated, expanded it, and I have calculated the overall transfer function. Now we are going to check whether the compensation we have done is correct or not. Right. So this is the comparison between the uncompensated and compensated. You put all stability margin. Now also the gain margin is infinity. You cannot see any point here. This is the uncompensated system where the phase margin was 18. Now the phase margin is 65.9. So this is greater than 50 degree. It achieves your specification. Gain margin is still infinity since it doesn't affect your phase margin. So that is fine. We don't have to tune your gain margin. It's always greater than 10 degree, 10 decibels, and your steady state value also has been achieved. So overall, all your compensation has been achieved. Now, just to understand the nuances behind this, I'm plotting the responses of this system, compensated and uncompensated system. Just letting you know what I'm doing is, this is the only the controller transfer function. Sorry. Yeah. Um, Overall compensated transfer function. So I'm just plotting the step response of the system first, unit step response, and then I'm doing the unit ramp response also for the same system. We'll just see what we are getting for this. These are all the two things you are getting. Now, you see this. This is the uncompensated systems response, where orange is the compensated systems response. So if you see the settling time, this is very far. It's take a lot of time to settle, whereas the compensated system settles quickly here. So this is your unit step ramp response of both of their system. Just to see, there is nothing we can take home from this. Just from the step response, you can see how well the system is being regulated. So you can play around this settling time, rise time. even though we use frequency response based techniques, we were able to finally achieve whatever response we decide to achieve, right? It was indirectly represented using the phase margin, gain margin, but to have those phase margin and gain margin, this is how your system output response. That is what the overall takeaway from this system technique. Similarly, I wanted to cover the lag compensated technique also, but we are running out of time. I will just quickly tell. I will quickly go through the important points. In another 5-10 minutes, if you can spare, otherwise you can see the live session. Right. In terms of lag compensator would look like similar structure, but your overall beta value would be different, where beta will be greater than 1 always. So if I take a system, for example, I'm taking a system like this, S into S plus 1 into 0.5 S plus 1, right? So now the specification includes your KV should be 5 second inverse, phase margin should be at least 40 degree, gain margin should be at least 10 decibels, similar thing. Now I have plotted the Bode plot for the system. First, we will just try to compensate for your steady state value. KV is equal to limit S tends to 0, S into G of S. This will give me 5 limit S tends to 0, S into 1 by S into S plus 1 into 0.5. So K by 0.5 S plus 1. So S will get cancelled. K by 1 into 1. So K equal to 5. This is what the, so your uncompensated system will look like this. 5 by S into S plus 1 into 0.5 S plus 1. Right. Now I have step 2 is to plot Bode for this system, uncompensated system. So I'm plotting that. I will show you how my, right. So this is my second system for lag compensation problem. Right. Now when I plot this, yeah, when I plot this, this is the Bode plot of our uncompensated system. So if you see there is a gain margin here, the gain margin is minus 4.44. We need at least 10 decibels. It is minus 4.44. It's also far. And the phase margin is minus 13. This is also bad. So we need at least 40 degree, right? So we have to make a compensation here so that we will pull both of this. But if you see, you have to lift the phase margin. Usually we will go with the lead compensator. But here the gain margin itself is very low, right? So in order to pull the gain margin at least to 10 decibels, we are first trying to design a lag compensator. If it is successful, like if the designing a lag compensator to pull this gain margin itself will take the phase margin to 40 degree, then it is fine. Otherwise, we have to design a lead compensator in cascade with this lag. This is what the idea behind this choosing a compensator between us. Right. Now, We know our gain margin is minus 4.4, phase margin is minus how much it is 13. But our requirement is gain margin should be greater than 10, phase margin should be greater than 40. So we have to pull both. First, we are going to try with the lag compensation. Here, so the since we decided to do the lag compensation and also the gain margin, if you see, it's lesser than zero, right? It's negative, and you can say this gain adjuster system it's unstable because the gain margin actually should be positive. So we have to try to make the system stable by pulling it towards the right positive. And this addition of the lag compensator will also modify the phase curve of your body diagram. Addition of lead will change your magnitude plot. Addition of lag will change your phase plot. So we must, similar to the lead compensation, we must also allow 5 to 12 degree additional phase margin to compensate for this, right? So in order to pull from this to this, how much you have to add? Around 53 degrees you have to add. So I'm going to take more than that. And also, to avoid the overly large time constant for lag compensator, we should choose a corner frequency at omega equal to 1 by t to be around zero point 0.1 radians per second. So this is because this corner frequency is not too far below the gain crossover frequencies. And the modification in the phase curve will not be too small. Okay. So we add about around 12 degrees. I'm choosing because this it is in the negative side and going towards the maximum to allow the phase margin thing. So now the phase compensation I would get is around to pull to 40. So around 60, 65 degrees. I'm just keeping it around 65 degrees. So the first of all, we need to find the phase angle of the uncompensated overloop transfer function. This phase angle is how much it is? To omega equal to 5 degrees. So phase angle of uncompensated open loop transfer function is around minus 128 degree at omega equal to zero point 0.5 radians per second. So our new gain crossover frequency is 0.5 radians per second. So to bring this magnitude curve down to 0 decibels from minus 0.44 decibels at this new gain crossover frequency, the lag compensator must give the necessary attenuation, which in terms of minus 44 decibels, similar to that. So this will be 20 log of 1 by beta is equal to minus 44 beta. We will get some value here. So the next step is that the other corner frequency that you want, one corner frequency is 1 by t, and the corner frequency is 1 by beta t. So you will get omega equal to 1 by beta t you have to see. So 1 by beta t corresponds to the pole of the lag compensator. 1 by beta t is equal to 0.01 radians per second. We are fixing based on the, we are just assuming it to be, we are just taking it to be 0.01. And if it is not compensated, we will again tune these values. Okay. So your overall compensated gain would look like this: Kc into S plus 1 by 10 divided by S plus 1 by 100. It's 0.11, another one is 0.01. So your KC equal to K by beta as we did for lag compensation. So 5 by 10 is 0.5. Right. Your overall, this will look like this. So in order, instead of writing all this, I just put it in my transfer function. So you can see this. Right. Uh, so this will be 250, or it will be 0.5, right? KC is 0.5. Here, overall transfer function of the system. Now we'll see whether the compensation is enough. Right. The previous gain margin is minus 4.4. Now the gain margin is 14.3. So we shifted the body plot towards left and added the phase. And the previous gain margin, sorry, phase margin is minus 13. Now the gain margin becomes 41. Exactly little bit above 40, but that's enough. No need to adjust anything yet. Right. Now we have satisfied all the requirements of the system. Okay. So if you want to see the unit step and ramp response, I will show unit both because this is a fifth order system. So you can see well with the ramp response also. Right here, if you see, this is your uncompensated system that requires so much time to settle and it has oscillations before it settles, and the peak value is also high. Here, this is the compensated system where it settles smoothly without any too much oscillations, and the settling time is also comparatively less since the phase margin is only 40 degree. This settling time is little larger than the one we saw in the lead compensation, that is 50 degree phase margin. So this is fine, right? We achieved the requirement. Okay. I want to tell two things. Lead compensation, lag compensation. Lead compensator increases the gain crossover frequency. This increase in frequency means it increase in bandwidth. So this implies the increase in speed of the response. So the response was quicker, right? For example, if you see this, this was like this. This looks very bad. Oh, it look like this, right? If you see the lag compensation, this decreases the gain crossover frequency. Bandwidth is also reduced. This decreases the speed of the response. That's why.
And your screen is not visible.
Oh, it's not visible. Okay. Thanks. I forgot to broadcast here. Right. This is what I was telling. So when we compare the lead compensation and lag compensation, lead compensation increases the gain crossover frequency and thereby it increases the bandwidth. So the speed of the response is also faster. When you design a lag compensator from the uncompensated system, the compensated systems has very less gain crossover frequency. Thereby, it reduces the bandwidth and it reduces the speed of the responses. When we plot the step responses, it look like this, right? So this is of lag and this is of lead. So this is the practical implications of the lead and lag compensator. So how well you want your system to be designed using this methods, you might want to design the system. So when do we record a lead and lag compensation? That is another question I used to get. So this is a kind of cascade compensator, and it need not be lead lag compensator. It can be one lead followed by another lag, or one lag followed by another lead. That can also be there. So in terms of adjusting the steady state and transient response, if you want to work on both, for example, in the last lag compensator design problem, you didn't get proper gain margin and phase margin. So in that case, you would have to change both of the system. So first focus on one thing. First focus on gain margin, design a lag compensator, and see if you get the desired specification in your transient response also. That is in terms of phase margin also. Here we got it only with the lag compensator. It pull the phase margin from minus 4.18 degrees to 41 degrees only with the lag compensation. But in some cases, this won't come. For example, the phase margin might be still around 20 degrees. So you would not get 40 degrees with only this lag compensation, whatever value you design. So at that time, you can change the values we assumed, like 0.01. You can change the value and see, but sometimes that will also be not helpful. So at that time, you have to design another lag compensator in addition to this, another lead compensator in addition to this lag, or both the ways. For example, if you work on phase margin first and you couldn't pull the gain margin, you have to design another lead compensation in addition to this lag. So that's how you will do all this lead lag combinations. First, do step by step. First, do check the uncompensated system's specification and try to change the gain value K according to your steady state responses. Then design one compensator and see how well it is being improved. Then design another compensator if required. These are all the overall steps to design your compensator based on the frequency response analysis. So that's it. So if you have any doubt, you can ask. Otherwise, we can conclude this session.
Ma'am, can we share a MATLAB script?
MATLAB script. Yeah, okay. I can share it. Thank you.